So intermolecular forces in action. Surface tension, viscosity, and capillary action are all due to intermolecular forces. Here we have two photographs. This is a trout fly floating on water, even though it is more dense than water and should sink. Here's a paper clip floating on the surface of water, even though it should sink because metal is more dense than water. You see how the surface of the water is kind of curved in here? It almost looks like there's a skin on the water that it's floating on. Like this was a pool with a cover on it. And then here you've got someone laying on the cover. And so they don't break through because there's this kind of skin, there's this covering on it. Surface tension, you got a question?
Yeah. Well, then is that also related to like why those gecko bugs can run across the water?
The little water skaters?
Yeah.
The water skaters can do it because they're on top of the water. They're not breaking the surface tension.
But is it because they're going really fast, or is it just because...
So you're talking about the lizards or the bugs?
The lizards.
The lizards.
Yeah. Is it because they're just going that fast across?
Part of it is the speed. Yeah. I've seen 2 shows about that, and I can't remember the conclusion of that. But all of these weird things that we observe in real life, they all have a scientific explanation, even if I can't come up with it right now. Surface tension is the tendency of liquids to minimize their surface area. It's quantified as the energy needed to increase the surface area by some unit amount. So water has a surface tension of 72.8 millijoules per square meter. That means if you're trying to increase the area of the water, the surface area, by a square meter, it's going to require 72.8 millijoules. So the surface tension, this tendency to minimize surface area, is what allows trout flies to float and water skaters to skate. How does this happen? Here we have a cross-section of a liquid, and here we have our liquid particles in blue. They're interacting with each other. They're attracted to each other by intermolecular forces. If they were not, it would be a gas, right? So we've got intermolecular forces holding these particles together. The particles at the surface, this particle in the illustration, is only interacting with 4 neighbors. The molecules in the interior are interacting with 6. Now, of course, this is just a 2-dimensional slice, and so if you put that into 3 dimensions, you've got others as well, but this is just for an illustration. So if we're going to increase the surface area, that means that we have to make some of these interior molecules surface molecules, right? In doing so, we're going to disrupt these forces of intermolecular attraction. That requires energy. Nature wants to minimize energy. It minimizes energy, maximizes attractions by making the smallest surface area possible. To increase the surface area, you would have to move the molecules apart. And just think about trying to put something into the water, right? To put something in there and increase the surface area, you're going to have to break intermolecular attractions, and that requires energy. We see that the surface tension is smaller for smaller intermolecular forces. Surface tension is greater for greater intermolecular forces. The reason that water droplets are spherical is due to this surface tension. They tried to make a sphere because a sphere has the lowest surface area for the unit volume. This is a cool picture from the space shuttle. That's one giant drop of water. We think of water drops as teardrop shaped, right? That's because they're being pulled on by gravity. They're holding onto the faucet or something, or onto the end of your burette, and you see it falling. But after it lets go, it forms a sphere. And so this is one giant water droplet in space.
How do they do that? They just
Well, you release some water, and I think sometimes they get the smaller droplets, but if you push them together, they will go into one. You do it all the time. Yeah, they would prefer to go together. Yeah.
So water naturally clumps together then like that?
Yeah. It is cool.
So you know when you get like really, really small drops of water,
Mm-hmm.
and they kind of roll over the surface of the water? Is that because they don't really weigh enough to break that surface tension yet?
I'm not super familiar with that phenomenon.
Okay, you've never seen that before?
Little
Have you seen
water
that video?
droplets. Obviously, have not seen the video.
There's a video where they do a drop of water and you can see it, it goes down, and then when it pops back up, there's a small one, and it bounces on the surface, and then when it settles, it's the same thing over. It's actually a really cool video. You should look it up.
Well, we'll have to look it up during lab.
Okay.
Yeah, we'll have
It's
to look at it.
probably one of my favorite things I've seen now.
Another property is viscosity. Viscosity is the resistance of a liquid to flow. It's measured in a unit called poise, which is a gram per centimeter second. And I'm just kind of telling you that. We're not going to do anything with it. Viscosity is greater in substances that have stronger intermolecular forces. And so that kind of makes sense. If you think of what is required for a liquid to flow, the particles need to be moving past each other. And the easier it is for them to move past each other, the more easily the liquid flows. It also depends on molecular shape. Here we're looking at a series of hydrocarbons. So these are all nonpolar molecules. They only have dispersion forces. But we see that as the size gets larger, the viscosity gets larger. What intermolecular force is dependent on size? That first one.
Dispersion.
Dispersion forces, right? As the molecule is larger and larger, it's easier to disrupt or to get the electron cloud lopsided and get those induced dipoles. So that's going on. The other thing that's going on is these are all what are called straight chain hydrocarbons, and they all have single bonds. The single bonds have rotation, and so these are like pieces of cooked spaghetti or snakes. They're all wiggly and wobbly. And so if you have a really long strand, these are going to get tangled up with each other more than short strands. Or you could think of it like hair, right? Short hair doesn't get tangled. Long hair can get really nasty tangles in it because it can wrap around. And that can happen with molecules too. They're more likely to get tangled up with each other. And so it'll make it thicker. Viscosity depends on temperature. I don't have any pictures of viscosity. Think of honey versus water. Which one pours more easily? Water, right? Honey's thick. It pours really slow, right? Because the forces that are holding those particles together are stronger, right? That has more to do with, yeah, if you heat the honey up, it'll flow more easily, right? So when you heat molecules, they have more kinetic energy, right? And so now they're more able to break those intermolecular forces. So heating decreases viscosity. Viscosity is really important in motor oil, right? You need oil in your engine of your car to lubricate the moving parts. You don't want it too thick, because if it's too thick, there are some places that it won't go into, and other places where it being that thick, it's not going to lubricate very well. But you don't want it to be too inviscid, too liquidy, or it's just going to fall to the bottom of the pan and it's not going to coat the parts. So you want this sweet place in the middle, just the right amount of viscosity. One of the problems with motor oil is as it gets older, you get viscosity breakdown. But you also have this temperature dependence, and that's why there's all these different grades of motor oil. Some of them are more appropriate for using in your car in Minnesota in the dead of winter, and others for driving around Fresno in July, right? Because at the higher temperatures, the oil gets thinner. And so if you have a thick oil, a viscous oil, but you use it in Minnesota and it's 40 below, it's going to be so thick that your engine is not going to move at all. What's really cool about the modern motor oils is that they've incorporated polymers. And these polymers will coil up at low temperatures, so they're more spherical, and so the intermolecular forces between them are weaker. And then at high temperatures, they straighten out and become more tangly. And so when the oil is getting less viscous, because they're spreading out, it increases the viscosity. And so these polymers will moderate changes in viscosity. Isn't that cool?
Mm-hmm.
That's crazy cool.
It really depends on where you live. You know what kind of oil you live. What temperature is it?
Well, yeah, temperature, I mean, part of it is, your specific engine too. But, in the winter and in the summer, especially in Minnesota where it gets so cold in the winter and it gets pretty warm in the summer, you need to match your motor oil to your driving conditions.
That's so cool. I learned about that in also
Yeah, yeah. So, I tell you about things like motor oils because I want you to understand that there's chemistry everywhere, right? There's chemistry everywhere. Another one is capillary action. Capillary action is the ability of a liquid to flow against gravity up a narrow tube. So here we have a picture of several capillary tubes, very, very small inside diameter. You stick the tube in this liquid and the liquid creeps up. It's going against gravity. How does it do that? Well, there are two forces at play here. There are cohesive forces and adhesive forces. Cohesive forces are the attraction between the molecules in the liquid. That's what's minimizing surface area, causing liquids to form droplets, etc. The adhesive forces are the attraction between the liquid and the surface of the tube. So here, the water molecules are attracted to the glass, and so they will creep up. And that's what's causing a meniscus, is because at the edge, you see the water molecules crawling up the glass. When they crawl up, the cohesive forces cause them to bring the other molecules with them. And so when you have a very small diameter here, you have a very small amount of mass that is being pulled up, and so you get a noticeable rise. Here, the tube is larger. And so in order for the water to creep up, it has to carry more mass. And so the height that it will reach depends on the mass of the liquid that it's pulling up behind it. And if you remind me, we can make some little tubes and see this happen in lab today.
Didn't we see it last lab? With the chromatography?
The chromatography, it's a similar concept of the liquid crawling up the paper, but it's not exactly the same. And here we have water and mercury. Here we have the concave meniscus. Remember when we look at a burette or a graduated cylinder, we're measuring to the bottom of the meniscus, right? If you put mercury in a glass tube, the meniscus curves the other way.
The attractions between molecules are stronger.
Yeah, because it has stronger cohesive forces than adhesive forces. And so the mercury doesn't like the glass, it likes the mercury, and so it's trying to make a little sphere here and keep to itself. Here, the water likes the glass more than it likes itself. And so it's creeping up the sides, right? And so different liquids are going to have the curve be different. Some of them in a glass tube are going to have a flat meniscus because those forces balance out. And if you have plastic or you coat the glass with different things, you can change the shape of the meniscus.
What would you have to use to make water?
To make water do this, you'd need something hydrophobic. If you coated the inside with wax or something like Rain-X, why does Rain-X make the water come off your windshield? It creates a layer that does not interact well with water. And so the water is repelled, it forms its own little spheres, and they just roll off.
explain that we're doing this. Nissan invented a new paint that is resistant to like mud and water, so it just slides right off.
Cool. You probably can't sit on the hood very well either, because you'll probably slide right off.
I don't know, but I'm pretty sure it has a lot to do with what we.
Yeah, I'm sure it does, yeah.
So is the Rain-X non-polar then?
The Rain-X would be nonpolar, yeah. Now, in your contact lenses, you want the opposite. You want hydrophilic, water-loving, and so in your contact solution, you have substances that help to coat the plastic contact lens so that it will be friendly to the water in your eyes.